Okay, so when we have the dichotomous variable, when we have something that has the disease, no disease, present, absent, we create this contingency table. And you'll see this a lot in epidemiology. It's just when you have that categorical dichotomous outcome, it's easier to put it in a contingency table. And then because we only have these four options, we're really going to look into the odds. So this is what we did, third class, I think, we looked at the odds, which are simply the probability of having an event relative to the probability of not having an event. So the odds of getting the disease when you have the risk factor, that's this first one. So when we have the risk factor, what's the odds of getting the disease to the odds of not getting the disease? And then we compare that to the odds of the disease without the risk factor. So right here, and we get the odds of getting the disease with the risk factor relative to the odds of not getting the disease. And those values are calculated right from the frequency from the probabilities that we did. And these are all this probability of having the disease given that you have the risk factor. We're familiar with all these terms from earlier in the term. And then because we're doing our calculus and we're using hypothesizing, we're making predictions about the actual population, we're going to have these as our odds. These values here, the imaginary number e raised to the beta naught plus beta 1, are the odds of the disease with the risk factor, and then the odds of the disease without the risk factor is just imaginary number e raised to the beta naught. Don't worry about those terms. I'm just showing that so that people that are more inclined to calculus can understand how we got those values. So we get these and we get the odds ratio, and that is what we use in logistic regression. And we just put the odds of the disease with the risk factor over the odds of the disease without the risk factor. So we're seeing how much having the risk factor impacts your odds of getting the disease. If it's greater than 1, you have more odds of getting the disease when you have the risk factor. If it's equal, there's no increase in odds. If it's less than 1, you have higher odds without the risk factor. So with logistic regression, the similar types of information, and it's that the odds ratio for a variable in logistic regression represents how the odds change with a 1 unit increase in that variable, holding all other variables constant. So the same interpretation that we made as the independent variable increases by 1 unit, the outcome variable will change it as the value will change equal to the value for the coefficient. In this case, the outcome variable is always those odds. So your odds are changing in relation to the increase in the variable. So let's look at another example. This is looking at vaccinations, and they surveyed 365 public health residents, and the citation's at the top of the page if you want to read it. It's pretty interesting. So if you look at it, about 52% of the people surveys didn't have any information about influenza. 28% said they had read scientific papers, and then excuse me, about 64% said that they had recommended influenza. So this is the survey results. And then we're going to look at the odds of giving the vaccine or not. That's what they were initially interested in looking into. So what are the chances, what are the odds that you, as a resident, give the vaccine or not? And that's the input characteristics that they feel are important to that are gender, age, year of residency, and then their information they have on the vaccinations, and then do they get vaccinations themselves? So they took it during 2 different seasons to see, and then they created this reference or adjusted odds ratios, which is if there was more males or females. So all that is adjusting for a differential proportion within the categories. So you want to always use those adjusted odds ratios as opposed to the crude. So before we advance, go ahead and think about what's the outcome variable, and what are the units, if any, and then what are the input variables and what are the units. Okay, so coming back, we look at our table again, and we see that the input variables are gender, which is dichotomous of male or female, age, which is years, it's categorical, years of residency, categorical or ordinal. Influenza vaccination is categorical, so is the participation in the vaccination campaigns dichotomous. The outcome variable is dichotomous, yes or no. So it's unitless. And we start looking at the results. So if you see here, we have the odds of having the vaccine, of giving the vaccine is associated as 3 times higher, almost 3.5 times higher if you're a male. So giving the vaccination is strongly associated with being male. Increasing, so in our typical interpretation, increasing the gender from 0 to 1, which means going from female to male in this case, increases the odds by about 3.5%. If we look here, we get increasing the age from being young, less than 29, to being slightly older, between 29 and 31, increases your odds by 0.86. So that actually is a lower odds. You're less likely to give the vaccine if you're 29 to 31. And then if you're above 31, your odds increase to 1.48. So, and this is all in comparison to that reference person. So the odds of giving the vaccine for a 31-year-old, someone over 31, is 1.48 higher than someone less than 29. And that's how you interpret those values. And they have the confidence interval, so you can also say the increase in odds for males the increase in odds of giving a vaccine for males is somewhere between 1 and 2.73 higher than for females. And this is what that data, going back to that original example with credit score, this is what the logistic regression equation looks like. It has that logarithmic growth. It identifies with those 2 clusters, but then in the middle it kind of has that curved and nonlinear association. And that's because our logistic regression equation looks like this, which is a logistic expression of our line. So this is what it looks like. I know it looks scary, but if you look at it, there's a lot of things in here we've already seen. So if you look at that, we have our beta naught, beta 1, x1. This is all the things we've seen. And the same way we just were interpreting them, we continue to do so. So if we have an increase in x1, if we plug in x1 values, we'll get a predicted y value. If we increase x by 1, the odds will increase by the beta 1 value. So it's nothing to be scared of, and just remember that the outcome is always the odds. When we're talking about logistic regression, we're looking at the odds. So let's do another example. If you go to your D2L and open up the EEL document, the EEL regression, logistic regression, we're going to run logistic regression. So we go to our regression, analyze regression, and then we go down to our binary logistic. And so we put our dependent variable. This is a study looking into, this is from your example. You can go look more at it at page 773. So it's looking at the odds of being cured having this EEL intervention, or not. So those are our covariates, which you can think of as your independent variable, and then our dependent variable is our curved. One thing that's different about this is if there's a categorical variable, you have to tell SPSS. So you click on categorical and then you want to pull over any variables that are categorical. Intervention is categorical. It's either have the intervention or you don't. So we put this in, and then it gives you the option to identify a reference category. So in that last example, when we had the age categories, the reference category was the youngest age. So you want to put whichever one you think is the least likely of having the outcome as your reference, because then the odds will increase as you go up that category. So if you have a placebo and 3 different types of treatment, you're going to put that placebo as your reference category. So here's the reference. We can put first. If it's the youngest age, you'd put first. So however they're listed from 0 to 1 or 2 or 3. You want 0 as that first. And you'll hit continue. So this will give us our data. And there's a lot of things in here that I can help you through if you wanna learn more about them, but I just want to kind of broad stroke this. If we look at the classification table, this is if there's no intervention, there's no outcome. We're just looking at the chance of being cured if you have nothing going on, and that's 57.5%. So if there's no intervention, half the people are going to get cured anyway. And so eventually we'll compare that to our model, which is our block 1, method, enter. So this is our model. And we go through and we see similar types of things. This is our R-squared value, and it means the same thing. About 11% of the variability in whether or not people are cured can be explained by this treatment and the duration of the treatment. That's one thing to look at, the R-squared value, same interpretation. And then here we have our classification table, and this is our contingency table, which shows the overall percentage of people being cured with the treatment. So it's higher. So now let's see, looking at our table, our variables in the equation, we're going to have the same types of interpretations, remembering that we're interpreting it for the odds. So we go to our beta values, excuse me, we go to our beta values here, and we see that the intervention, as it goes from not having an intervention to having the intervention, the odds of being cured, that increases your odds of being cured somewhere between, if we go over here to our exponential B, these are the actual confidence intervals for the odds ratios. So we have these beta values that represent the relationship, but these are the ones that you actually want to interpret here. So this is the effect it has on the odds. So we see here that intervention is significant, so we're going to include that one, and we're going to say the odds of having the eels treatment increases your odds of being cured somewhere between 0.129 and 0.656. The duration is not significant, so we won't include that one, but we will include this one. So if you were reporting these values, you would say duration was found not significantly to affect the rate of cureness, but intervention did have a increase in odds of being cured somewhere between 0.192 and 0.656. So that is logistic regression. Again, I'm not too worried about you guys doing the actual math of it. I'm more interested in you just knowing when to use it and then how to interpret the values from it. So you can expect a graph or a table of results and possibly a question about how to use it and when to use it. But don't worry about the math behind it or the sort of fundamentals. I just wanted to introduce you to it. Okay, thanks, and I will see you guys next week. Let me know if you have any questions on all this, and I'll do a brief review when we start class next week. Thanks.